so I'm part of the team in Teradata, which is focused on doing a lot of innovation research and then converting this into a product. So when Sab was showing you the Unlimited, this is, for example, the product that came out of TIO and is now in engineering being deployed. So we have one benefit. We are not so much restricted by timelines, but we also try to deliver those results faster, and we can experiment more. So what I'm going to show you is the ways how we develop prototype and tested this prototype, just to prove the point initially on 10 million documents, but we are planning to do more tests on larger scale of documents. But before I go, I want to ask a simple question, like how many of you understand roughly the word vector embeddings? All right, so it's not bad. So for those who don't understand everything, in oversimplification, the vector embeddings represents the representation of meaning and the relation between different elements. And in the nature, we can see the word embeddings, sentence embeddings, user embeddings, image embeddings. There are different embeddings or things you can embed, and then you define mathematically the relation, which is the distance between them. And from that perspective, there's a number of different use cases. And again, from me, I believe the vector embeddings will, at some point of time in the future, go beyond what we have in the hype today of being just the Gen AI type of use cases. I think a lot of ways databases will leverage embeddings to enable SQL algebra to query non-structured data like binary files or pictures. Because in the past, we had to parse them, we have to really work with them, understand how we can represent the image. There was multiple attempts to do the SQL against the image, but in reality, it was always the failure. I think with the embeddings in the future, we're going to see a lot of demand for ability to join a regular data like tabular data with the embeddings to give us more cross-data use cases. As you can see, a lot of those use cases, they're sort of centered around the similarities and finding the relations and similarities between different elements. Like in NLP, it's been about the words, the sentences. It also could be about the user behavior. You can also vectorize logs and see how the users are behaving and leverage the similarities to find fraud or some form of hacking or some weird behaviors of the users. So it's becoming a very useful element. I'm a huge fan of bioinformatics. This is my close to me topic. So I see a lot of development also in the space because people are trying to go beyond just the language being a natural language like English or other languages, but also using, for example, proteomics, genomics as a language. So trying to define like a new languages and then training the models for the Gen AI to operate on the language being, for example, genomics and proteomics. So as you can see, there is a lot of use cases. And this is why we wanted to see how Teradata can really be in this. So what is interesting, we initially said, can we really do embeddings? And we realized we can do the embeddings today. And this is what you saw on the main stage. We use the standard TD vector distance function, storing embeddings per column. But that comes with certain limitation because we were limited by 1,500 dimensions. So we started to see, can we do this differently? But we wanted to first find what would be the use case we want to experiment against so you can tell us how we should approach the problem of indexing and also make it user-friendly. And this is where we focus a lot on the RAG architecture. This is a very oversimplified version of RAG, but I wanted to set the stage. So today in the RAG space, of course, we are operating on the corpus. Corpus could be a documents, could be a files, could be a text, could be anything you want, which is normally called corpus. And then what you do is you convert this corpus into the text, you define chunks, and we will discuss a bit all of this. And initially, people were focused on using the embeddings-only search, so using similarity search, but they also realized that there is a growing cost factor related to this. So people also see that maybe we should be using a ranking search, which is basically a mixture between the similarity search and the full text search. Now, as you all know, databases are not always perfect in a full text search. So we are doing another set of experiments if we could implement BM25 algorithm into the Teradata. But what we're going to do today is focus on the embeddings. So generating embeddings, being able to store embeddings, and do the very quick retrieval at scale of those embeddings, and how easy it is for your users to use Python on that. So that's why I wanted to have this oversimplified version of RAG so that you can understand what we are doing and what we will cover today. So when we started the experiment, and I was talking to a lot of universities, a lot of customers, everybody was saying, oh, we started doing the Gen AI. We loaded 10 documents. We loaded 100 documents. We loaded 1,000 documents. And when you're building the corpus on smaller number of documents, it sounds very easy. You can just download PyPy, some one package, and suddenly you have a PDF converted to text. But then you start taking this topic really serious, you realize that's not as trivial as it sounds. Building corpus, it's a really complex task, and it requires a lot of experimentation. And believe me, single Python package doesn't work. If you think it works, believe me, it doesn't. So in reality, what you can think of building corpus, that's why I said that extracting text is not as simple as it sounds. It can be built based on multiple steps. So the step one is we have to export the text. So if we take a PDF as example, book or research paper or any document you have, we have to extract the text. So connect to the sources, which could be multiple files. Now we have to handle the concurrency of this process. Now extracting text is problematic. Sometimes PDFs are very well defined, very easy to extract. But what if the PDF represents the scan of the document? Then the average PDF SDKs cannot handle the conversion. So sometimes you have to do something what we call the high-res extraction, which is the combination of extracting text, OCR of this document, doing YOLO on image processing, then extracting tables, formulas, everything, converting them to base 64 so that you can maintain the details information of all the relevant information. Because what if your PDF document has a title and a monster table? The PDF to text will give you title and very weird-looking table as a text. So this process sometimes requires some more GPU, sometimes can be run on CPU, but it also has to be run in parallel. As example, when we initially built the pipeline and we ran this on the bare metal system as experiment, we were seeing like spikes, 100% use of CPU, then suddenly it was going down because the Tesseract was doing OCR processing. So we had to build a full parallelism to Python, and then we found there are different parallel frameworks between the cloud and on-prem and all this stuff. So those things you have to think, but what I'm trying to say is there is a ways, but it's also don't assume that you can just export text from PDFs. It takes time. The second thing is you have to think of, do I want to transform this text? So the extraction process will give you everything. Now the question is, do you really want to have 800 footers in the same text and then generate embeddings for those footers or headers in the document? In some cases, you may be not interested in pictures in your text. So maybe you don't want to do the OCR. So those are things you have to filter potentially out of the outputs of this. Then the storage element, where do I want to store the information? There is another interesting element is, in some cases, when you run your generative AI model or ask the question, especially if you, for example, assume that you are transforming big documents, 800 pages, and you ask the question, you get answer. And then you ask the question, what is your source? You get a title of the document. Sometimes you want to see which page represents the given text I'm asking about. And that means you have to reorganize the text into chunks per page with certain form of overlaps before you even do the RAG chunking process. So those things you have to really take to account when we are building the corpus. So one of the last steps is chunking. And again, what is interesting, when the Gen AI started, everybody was talking about the fixed weight chunks, which is basically say how many characters do I want to cut for embeddings generation. Then people say maybe we should do sentence chunks, but that's also create the problems because sometimes the sentences are very small, and then what you do with the titles, and there's a lot of complexity in doing the sentence-based chunking. I like the recursive chunking, which is basically you define the size of the chunks plus the overlap, because that gives you a certain sense of not losing meaning of the paragraph of element. And there is a growing element of semantic splitting, which I would say, if you are willing to invest to having 3 times engaging the LLM, I'm all in for you to go and do semantic chunking. It's a very good, very effective method, but it's basically requiring you to use LLM to chunk the data which you're going to use for LLM later as embeddings. So the semantic chunking looks the way that you submit the text to LLM and you ask for summarization. And the result of the summarization is your input to the chunking so that you can generate embeddings. So you like basically engaging LLM as a part of the pipeline in order to engage LLM for the answers. It's a very effective method, but depending on your budget, and if you listen to the presenter from the Microsoft when he said sometimes budget is a constraint. So we have to think how much in the initial pilot we really want to go into the very effective way, but very expensive way. So in our experiment, we used recursive chunking because that was the most effective one we found when we were exporting 10 million documents. Now, enrichment is the process which is recently added because of the contextual embeddings, where people are talking that maybe I want to summarize embeddings, and instead of doing the similarity search, I can do basically a search based on the context of the whole sentence and so on. So there are some other steps. And now, once the corpus is built, the next step is you can generate embeddings. Now, I'm going to cover how to generate embeddings because that's a relatively very straightforward process. What you do is you either have your own model or you pull the model from Hugging Face, or if you have OpenAI subscription, you can use OpenAI to generate embeddings. Embeddings then are being stored into the vector store. So what you saw on the stage, some of those examples from last year from Teradata, we use the standard way of storing embedding per column. As I said, because of the nature of table, it was restricted to 1,500 dimensions. So what we've done is we use byte as a way of storing embeddings, vector embeddings. So that allows us to store 32,000 dimensions per single column. That's also, we found, is the most effective way for us to have higher performance of using the k-means and IVF index on the scale of running multiple clusters. But we said there also may be cases in the future where we want to leverage var byte. So that's why I'm saying this byte and var byte. We focus a lot when we develop this on byte because that's give us the highest performance. And this was as closest to the way how people are using Python and seeing embeddings today. And that's give us a very high ways to store this in the Teradata system. And then, as I said, we have to rewrite the k-means function. We also, as a part of doing this, we learned that we need to build a micro-batch k-means function. Because the problem with the building k-means-based index like IVF is that if you have 10 million documents, if they are really small documents, you have only 130 million rows of embeddings. If they are larger documents, you end up having trillions of rows. So calculating k-means against the trillions of rows may generate several thousands of clusters. This process will be very long. So we wanted to have a process which allows me to generate k-means on the smaller subsets of the data so I can have an incremental process of building the index. When we build the IVF, the inverted file index, we also added element which is automatically triggering rebuild of the index so that you can decide if you want to use the brute force, which is the full scan of the similarity versus using the index search. That gives you different choices. We also look at other techniques. I don't want to bring this up. We decided to stay for now with the IVF and disk ANN, but we are experimenting with other index types. You have to remember, being a database brings also certain restrictions. So we cannot use some of the in-memory index structures because of the way how we handle parallelism. So this is why, for example, we don't use ANN, we use the disk ANN because disk ANN allow us to have a higher performance with lower memory usage for consumption. And I said, so we built all of this, and then we sit down and we said, can we scale? So we said, let's run the test and see how it's going to work. But then we also noticed that nobody in the AI community likes to use SQL. They all like to use very specific form of interacting with the vector stores. So we said, let's stop for now some of the other advanced work we want to do and build a way for us to expose this vector store as almost like a Python native as well as LangChain native implementation. So that if you have a user who is used to using different vector store or have a RAG pipeline built in Python, he don't have to go and study how Teradata is creating the index. He should basically go and call this in the way how Python users are interacting. And this is why we built two Python modules, one called TD Vector and one called LangChain TD Vector, which basically allow us to create this easy way to integrate Teradata into your existing RAG pipeline. So you can really test with this. So let's start with the TD Vector. I have a few coding slides. If they're not very visible, I think you will be able to get those slides. If not, you can always contact me, and I'm very happy to give you the full synopsis on high-resolution code, how this looks like. So the step one is we have to configure the embeddings model. So in this case, we are using the GT-based model. We specify the table name, and then we have define the dimension, define some metadata about the table, as well as we want to store in the results what type of model was used to generate embeddings, so that you can always come back and check on your embeddings table which model was used to generate those data and build the index later on. Then, so you have to define the schema. Once the schema is defined, you basically can force recreation of the index. As I said, we build a trigger on the table the way that if there is more new data coming, it will automatically trigger a build of the cluster ID, or push the process of rebuilding the whole index in the background. But if you don't want to recreate the index, you can also always start by saying, I don't want to use the index. Maybe I want to use what we call the brute force search. So brute force search is basically you are not searching based on the index. You are scanning the whole embeddings table, looking for different similarities. If you want to create the index, you can specify, basically call the package TDV, which is the Teradata vector package, and then say create IVF index, the name of the index, the IDs, and then define the distribution, as well as how many iterations you want to do. Why? Those iterations are very important. So it's a judgment you have to make at some point of time. You will get higher response time or lower number of iterations. And that will, so for example, on the number of iterations 8, the accuracy you will get on the similarity search is close to 0.8. If you increase number of iterations of the building the index, your accuracy will go to 0.9, but the performance will degrade. Not dramatically, but depending on the type of SLAs you have on the retrieval, that may influence. So sometimes you have to make this judgment. Do I need higher performance, lower accuracy? Not that low, but lower versus higher accuracy, but smaller performance, because I have to do more intense computation and define more clusters for that. But once the index is built, we can use the index. So the next thing is we are just adding, this is Azure LLM just for the example. And in this example, you see SQL code. But what this represents is we didn't want to ask the simple question. We had a MS Marco data set, so we basically submitted a table with all the queries. So we wanted to basically submit multiple queries at the same time and see how fast we get multiple resources and responses without us typing the query. So we really wanted to do this more systematic. So this table you see, it basically gives you the number of questions, which are the topics. So those are the questions, the top 5 questions we see in the Marco dataset. So MS Marco is a Microsoft dataset which you can download from Microsoft GitHub, which has 10 million documents, and there is a ranking table how fast different vector stores are handling the retrieval process. So we wanted to be fair and not to say to you, oh, we had this really good performance, but we use our highly customized dataset. So we wanted you to see how we operate on the MS Marco example. So now, once this is done, as you can see, in order to execute the search with the queries, I'm basically defining the doc IDs, which I'm saying I want to do the search against the embeddings table, specify the index. If you don't specify the index, as I said, we will do the full brute force search over the embeddings table. And now we basically call the doc IDs and search by submitting those 5 questions, and we are getting response time. So the average response time we are getting with the index is between the 20 to 40 milliseconds on the 10 million documents on the 2-node system of Teradata, which is quite good. Having said that, we are not doing any full text search, so this is not a rank RAG. This is basically a pure vector embedding similarity search execution. And we also test this on the larger system, so we wanted to see if I add more power, do I get linear scalability of Teradata? And the good news is we got the higher performance by adding more ARMs, therefore doing more processing, which basically more documents will require a bigger system, but you can maintain the SLA on the response time. So this is the TD vector. And then I said, because everybody also is talking about the LangChain doesn't, it's not that they don't allow you to use the Python way. LangChain has introduced a very specific semantic how to call the vector embeddings and index, so we had to follow their rules. So we implement our own Python module, which allows, as I said, plug in us to the LangChain Python process. So it's very similar. You specify the embeddings model. You define the connection to Teradata. You define the name of the table. And then you define the vector store. In this case, this is Teradata vector store. and again, you provide certain elements. The schema of the table is defined by LangChain, so there is a way to influence the schema, but LangChain prefers schema of the vector store to follow their schema, not to have your own schema. So we wanted to stay in the boundaries of them. So you define the vector store, and now what you're doing is, again, connecting to the LLM. I'm formatting the docs. Similar case, here I'm defining this is my vector store, this is my retriever. Is going to go with the index. And similar case, we have the same table with the questions. So you can see very similar code, just LangChain compliant, and we get answers. So as you see, except you showing me how to get the questions, the user do not see that all those functions, all those Python code like retrieve, document, create a vector store, they are all converted into the SQL. So the user do not see the SQL. We wanted to really abstract this as much as possible to make it for the RAG user, not for SQL users. Now, if you want to know the SQL, we will give you SQL. That's not a problem. It's just we knew that users will not like to write like a create data frame, run this SQL query, and then execute the RAG. So really wanted to make it RAG compliant as much as we can. So this is just a summary that so if you are very interested, we are more than happy. You can ping me, and we will discuss how we could give you access to this code. There will be more sort of releases of flavors of this code coming from Teradata in the coming months. But this is something you can deploy on Teradata. This is just a set of scalar UDFs, which we built in C. And we've done the help function in Python module called install, which basically deploys those UDFs automatically on your system, assuming you don't have restrictions from your DBAs and you're not allowed to install UDFs. But if you're interested, please contact me and we'll be happy to give you details. As I said, right now we have the IVF and this KNN, and we are looking at other indexes, but we are also looking how we could bring this full text search into Teradata by implementing BM25. But as I said, we focus more on a fact of storing embeddings and improving retrieval at the large scale of the data, which is important. There is a last topic which I want to cover, which is outside of the RAG. This is something we even have a pending patent on that. But the whole point was when GenAI or OpenAI created the first ChatGPT, when I was testing this, I found that there is something very strange. The GPT models, they do not understand time. They always operate on the latest information, latest document. If you ask them questions to define how things were evolving over time, you get a representation of the text which defines the history, but it cannot interpret the business information. And then I was like driving back from the office and talking to my team, and I realized that Teradata has a temporal feature. We can store embeddings. What happens if we combine both things together? Could we make temporal embeddings and temporal similarities? So we've done a few experiments. It's not as perfect Python code or Teradata code as you can see, but it's started to show us very interesting results. And as I said, the biggest challenge is that none of the models today understand time. And especially if you are dealing not with like books, even that books may change over time, I think in the form of writing like a GenAI applications on your standard business data, there may be an interesting element of I want to understand how certain things were changing over time. So for example, if you are in the healthcare space, understanding how claims were evolving, how people were putting changes into the same claim could be very beneficial. Where, for example, in LangChain, what will happen is every load of the claim will replace the whole claim and embeddings for the claim. So you will not be able to see how this claim looked a month ago versus today. So it's a very interesting, I think, prosperity which will have more traction in the future. You can say, OK, but there is a lot of buzzwords, especially in the past 3-4 months, about the time series LLMs. So time series LLMs are not talking about the temporalness of vector and similarities. They focus on executing time series functions and forecasting models using GenAI. So getting in the space of what if and simulation using different time series models, focus mostly on forecasting, which is totally different than temporalness and temporal definition of the data based on the business events which are changing those data. So right now what we've done is we implemented two elements. So we use Teradata temporal, and we are using business events to define almost like a build a CDC process in our old good Teradata data warehousing structure, where every time the row is changing, we store the previous version of the row and add the new version of the row. And then when we calculate embeddings, we replicate the same start and end dates, but we generated the new embeddings. And then we realized there's another use case where maybe not just temporalness of embeddings makes sense. Maybe I also would like to create the similarities. So depending on the use case, I may end up computing multiple similarities and see how does the relation between the sentences was changing over time, which may be less important from the legal perspective, like compliance perspective, or like claims or something. But I think there are some use cases where understanding change of relations in the words could be very crucial. So we're not saying you should go tomorrow and start doing the temporal embeddings, temporal similarities, but I think there is something in there. This is just a rough experiment where we basically store them. We now can query, and we can see that those embeddings are automatically historized. But then we also build and start augmenting the prompt screen. So we also get to the space where we are able to add prompt, where you are asking, like, can you tell me how this claim looks like? It will tell you the latest one. But if you will say, can you show me how the claim was changing over time, what you will get is the answer which segregates answers based on the business dates, and you will see the deltas between them. And I think in the future, that also will dramatically increase the speed of building corpus, because I said you would not have to replace full documents. We will be able to just replace the subsection of the vector embedding space and the cluster IDs without replacing the whole text all the time. So I think that is going to drive a lot of good elements. So use cases, I said, we had interesting discussions with a few of the healthcare providers. They found this interesting. Of course, a lot to be proven in terms of temporal embedding space, but I think it's very interesting. There was also discussion that could be a very interesting case if you're a healthcare provider for the denial cases, because you may see how and why certain decisions were happening on the document. So you don't just see the case was denial, period. You may see that what was the history, who was adding, who was maybe doing the denial versus should we come back and maybe do something to improve the customer happiness, or at least make them less not happy because we declined the claim. As an improve the overall embeddings process. And right now it's mostly for the compliance, but I think more and more we will talk to customers. I think we will learn and sort of stimulate more ideas how the temporalness could be used in this space. I'm also trying to work with professors at UCSD to figure out that could we start using some of the student projects to work together to find some new use cases, maybe for engineering, like the network stuff, or the machinery, like heavy machinery or material design, where sometimes understanding the time could make a lot of sense. But I think it's an interesting topic. That's why I wanted to sort of wrap it up with this as a history. I have a few takeaways. As I said, the key message I want to give you is, like, it's not that we are the vector store for everything, but we've done a lot of experiments, we've done this at scale, and I can tell you this is really hard. Like, people say, oh, it's easy, I can extract the text, I can run it. No, it's not that easy. It takes time. You have to really think about multiple dimensions. There are ways you can make it simple. You can use Adobe SDK, you can use portions of the unstructured.io, but you will learn very fast. You have to understand your data, and every time you have a new document, new source of information, you have to rethink the whole rack again. So it's really complex process, requires a lot of thinking. We are very happy to share with you the code we use for our experiments to load those 10 million documents and more. And we are now in the process of converting 100 million PDFs basically to text because we wanted to do the bigger test and see how this is really going to scale more and more. As I said, a lot of experimentation. So don't try to attack the world problems. Like, we are not going to change the climate shifts because we can do the rack. Downscale your problem, start thinking, experimenting, start moving, because you may be stuck in the document extraction for 1 month. And then we'll quickly learn that, oh, chunking required me to do the paging, so maybe I have to go back and redo the extraction. So start smaller, but experiment, and then start thinking, what if I go from 1,000 documents to 10 million documents. Is my rack really scaling? Because I can tell you one thing, which is funny. Parallelism in cloud is not the same as on-prem. Even Python parallelism is different. There is a huge difference between using pool processing versus multi-threading. And if you don't test some of your rack pipelines at scale, you may have some problems later on. So I'm just saying, like, experiment a lot, don't be shy, and experiment. As I said, you will see more and more from Teradata in the space of vector space, but if you're interested today, you have the one which we have, which is the column base, and you can contact me and we can discuss how to get access to this, because I'm looking very happily for any feedback from customers, especially your rack architects or users. Like, should we change something in the Python code or something? So I'm very happy to get feedback, and if you're interested in this, contact me and we will figure out how we can get you access, and there will be more releases coming naturally from Teradata. And I said, the temporal is a new thing. I believe it's not that because we come up with this idea, there's nothing dramatically novel in the sense of temporalness of data and embeddings, but if you combine both, I think it's opening doors to a lot of new use cases and the ways how to handle embeddings with understanding of the time. So I think it's very important. So with that, I'm very happy to take any question.
Yes, thank you very much. Hey, Arthur, thank you for a very interesting presentation. I have a question about one of the items that we touched earlier, one of the topics, and note in the end. The question that I had, if we can go back to the slide where you were mentioning that it is possible to scale the process of checking the embeddings and establishing connections, okay, through them by means of a nearest neighbor distance algorithm or whatnot. If I understood this right, my question is this. If I have my embeddings in the database spread across different amps, to find nearest distances, I would think that this is an all-amp task, right? So no. I would need to have all data together. How do we explain this?
Okay, that's a good question. So if you are doing what I call the brute force search, which is not based on the index, then yes, we are doing all-amp operation because we are scanning the whole table. We have done some tricks to do partition elimination, but it's very hard for us to understand because there's only cluster ID because we didn't define the centroids and the key centroids per cluster. When we do index search, it's a single AMP because we do the partition elimination, and it's because this is a columnar table, so we can very fast go to the given cluster ID and then find the given centroids and get the results back from the similarity. And for the text storage, we use object store. So we join embeddings result by the document ID and the part ID with the text in the object store using for-each table, and that gives us the retrieval time.
So the information. One, two, it works. Even without electricity, that's amazing. Sorry, so you're actually suggesting that all the data are in a single column, therefore it's not needed to be partitioned across different processing units, or is it just the indices that carry the information?
So we do that, we do two levels. So one is the embeddings it's not multiple columns, so the embeddings are stored in single column.
Okay.
But then we do the second level partitioning on the cluster IDs. Because we use cluster IDs for two reasons as a result of the k-means. One is because we want to refresh the index. So if you change the data in the given cluster, we just replace one cluster in the index. So that's why we use cluster ID as a secondary index. And then for search, we do cluster ID, and which basically give us the distribution of centroids, and that's give us the result. So we can basically do the partition elimination, and we don't have to scan the full table with the index. Even with the index, we can do partition elimination on the index, and then basically do the retrieval, which is a single AMP operation.
So to translate in plain English what you said, the algorithm can be adjusted.
Yes.
So that I don't have to deal with the fact that I need to do split, partial computations, and then that sounds great. Thank you. One last remark. Some homework for your LLM model. Do ask it to dig out my dissertation, what my dissertation was in.
Okay.
I have a quick question regarding the process. So do you need to put in all the documents that you need to analyze upfront, or can you do it at runtime as well? So you've got all the existing one, or you just can throw a document it or a set of documents at runtime, it does the vector embeddings and then give you the answer?
So it's up to you, because as I said, the building index is the most expensive process from the Teradata perspective. So initial load will be always the nasty one, but you can do also. So this is the reason why the scale is important. So when we start initially, we said, okay, 10 million documents, load them. And then we realized that the k-means, which is used for IVF to build the centroids, is too slow. So that was a good experiment for us. So we had to rebuild the k-means function to work as a micro batch so that I can run smaller batches. So from that perspective, now after the final change, we don't really care if you're loading all the documents or subsection of documents. But we only found this because we've done this like, okay, we have 10 million documents, let's load them and see how this goes. And then we are running the index creation, it's taking really long, so we have to get something different. So the challenge is that in the future, if, for example, if you are updating or loading more documents, if the vector embeddings will end up in a single cluster ID, the refresh of the index is very fast. But if you start changing a lot of clusters or you dramatically change the distribution of the clusters, we have to rebuild the whole index. So the way we want to do it is the way that if the load is going to increase number or dramatically change the distribution of cluster, we're going to start building the index while you're still using the old index, and then we start refreshing the index. So we give you the choice, use old index, brute force, or wait for the new index when it's rotated. But there is this element which you cannot work around. You have to build the index. But the good part is the difference on the retrieval time is not that dramatic. Like index is improving more and more, especially in the larger data sets, and gives you much scalability. The brute force is, so for example, 20 to 30 milliseconds with the index. Without the index, we can go to 200, 300 millisecond retrieval time. And sometimes bigger, depends how big the table will grow with the index and how many clusters you have. So this Marco data set end up having 10,600 clusters out of k-means. It is, if you look from the k-means, it looks like a lot. From the rack, you know the distribution of sentences will be big, so it doesn't sound very big, but it's a web crawler data document.
Hi, great presentation. Excuse me, I'm not very well with this topic. I used to use structured database, Teradata, normal tables. But as I could understand, you have an index to find the text, to find, if I make a question to a task, I would read everything. So with this vector, I can find where is the answer to this question in the middle of a big document. Is that the objective of this?
It's sort of. So the complexity starts that when you ask the question, you have something which we call the similarity of words. So for example, you can have a dog as a word, and you can have the German Shepherd as a word. What the vector embeddings and similarity helps you find is that both words represent dog. So the topic you are looking for is about dogs, not about German Shepherds only. So it's about finding similarities between the objects and giving you answer based on how close is the similarity of those different definitions, because in the sentence it's how the same is the sentence. So for example, I'm not a native speaker, I have a California accent, but I'm not from US. So I make a lot of typos. To give you perspective, I cannot use typed chats in these banking systems. When I type or talk, they basically give up and send me to the person. In this context, what happens is over the time, the way I make grammatical mistakes by using my native grammar, sometimes by nature, because I was born like that, I make typos, I define questions in a different sense. The similarity will classify, oh, this is very similar to this English question, so you are looking for this information, therefore I'm going to retrieve and give you this information back.
Okay. Another doubt. You said every time that the documents were in PDF. Usually my documents are in Word. When I want to print, I create a PDF. Is there any difference if I input the Word
No.
instead of the PDF?
So if you want to experiment, I recommend people to look at the unstructured.io. They have a very brief description of different documents. So for example, Word document is very easy to parse because there is a metadata which describes it, so even table can be very easily described as a text. PDF is just, there's a lot of research paper, a lot of books, a lot of scans done automatically as a PDF, but you are not restricted to PDF. You can load emails, you can load whatever you want, basically, and convert to text. The extraction will be simplified because the metadata is there.
And the last one, when you said the chunks, I was thinking about each word, but you said chunk as a sentence. Is there a better choice instead of words is a sentence?
So it depends so that comes back to this whole accuracy of the whole sentence. If you're going to use sentence embeddings, then doing the chunking per word doesn't make sense. If you're going to tokenize per word, you could do chunks per word. There are people who try this and it works for them. It's really, that's what I'm saying, like sometimes you have to do multiple racks and see what works better for you in terms of chunking. Do you prefer, because sometimes you want to, so for example, if you do chunkings per word, you cannot do sentence embedding, so you have to, because you cannot define similarity of the sentence because you have the words being as an input for the vectorization. So, but if you are looking more for like, I want to more like a keyword type of search based on the similarities, then you could do chunking per word. It will just create a lot of rows of data. So maybe that's something what you need. So that's why the experimentation is very important. This is also why nobody today, even OpenAI, will not tell you what method of chunking is the best one. Like everybody has different methods. Everybody's telling this. I said, I like recursive one because I like sentence embeddings. And the recursive one gives me a size, for example, 1,000 characters plus the overlap. So if there is like a very long sentence, and it's cut by half, I'm not losing all the content because I can have overlap between the different chunks.
Thank you.
Okay.
If not,
all right. Any other questions? All right. I promise this is the last time I'll ask you to do this, but one more time, get out your app. Go into the Vector Embedding Store presentation, scroll to the bottom, and please fill out the survey. Again, thank you guys for sticking around till the very end, and one more big round of applause for Artur.
thank you.